All right, so in the previous one, you guys noticed that I ran out of time. But in this one, so the Doppler effect, once again, let's go ahead and say this is for stationary observer and moving source. So this is like, me standing outside the road and a cop car passing me. All right, when the source is coming closer or approaching, so closer or approaching, we came up with a formula that the perceived frequency by the observer will simply be the actual frequency all over 1 minus v of the source. So the velocity of the police car, the velocity of the moving speaker, the velocity of the object that's producing the sound towards us, all over v of the sound and air. Okay, that's when it's approaching us or getting closer. Okay, and so let's see if this makes sense. If the reason we have a minus sign is the source, if it's moving at all, this will be some fraction. 1 minus some fraction is going to be something less than 1. Right? So 1 minus that fraction is going to be less than 1, which means if the denominator is less than 1, that's going to make the perceived frequency higher. That should make sense. All right? When the object is still a stationary observer, when it's getting further away, all right, when it's getting further away, we got f prime was equal to f all over 1 plus v source all over v sound. Okay, and the plus sign means that this fraction is going to be, instead of less than 1, it will be greater than 1. Well, if the denominator is greater than 1, the perceived frequency will be less. And so further, we would expect us to hear a lowering of the frequency. Now, what's really cool is you can combine these two frequencies, or these two formulas, into getting this. So let's write this down. F prime is equal to f all over 1 plus or minus v source all over v sound. Okay, the key idea is you will use the minus sign. All right, let's keep this in mind. Minus sign when it's approaching, getting closer, and you will use the plus sign when it gets further away. Okay, and so let's box in that formula. Now that is the case when you have a stationary observer and a moving source. Okay, so now we're going to move on to the case where you have a moving observer but a stationary source. Okay, so imagine that you have a source that's right here, all right, and he emits a sound, and he is stationary. Okay, so let me say stationary source. All right, and you know what I'm going to do? I'm actually going to erase this, and I'll do this down here. So that's a stationary source, and I'm going to go ahead, and here's his first wavefront. There's the speaker, the thing producing the sound. That's his first wavefront. Then he's going to have, after some period later, that's that. Now this where it was is now there. Whoops, excuse me. Then after some later time t. So these all these, they're all lambda. Okay, the difference in here. These are the wavefronts, and the time it takes for it is the period. Okay, and so we know that the v of sound, right, is simply the frequency that is being produced times the wavelength that's there. Okay, so a stationary source. Then all of a sudden, let's say you are driving into it. Okay, so you're getting closer. So we'll say getting closer. Okay, well, this wavefront is moving to the right with that speed, and then you're getting closer with some speed. We'll say v of the observer. So v OBS for the observer. All right, so what I'm going to do is I'm going to say, hey, v prime, v prime, all right, the speed. So take a look. Imagine that you were still, right? You were still, the observer was still, and these things were moving. They would look like they're moving with that speed plus that speed. So this would be v of sound plus v of the observer. So imagine yourself like driving down the interstate. Actually, let me change that because I like the little script v of the observer. Imagine you're driving down the interstate, and you look over at the oncoming traffic, like on the other way, and you guys pass each other, if you're moving 70 miles per hour and they're moving 70 miles per hour and you're moving past each other, it's as if you're staying still and they're moving at 140 miles per hour. That's what you observe. So when you move into the wavefronts, right, it's going to feel like you're going to be hitting these wavefronts faster than you would be if you were just not moving at all or moving away. So because you're moving into them, the perceived velocity that you're moving with is going to be the addition of both of these. All right, and so you're going to perceive some frequency. So remember, f prime is the perceived frequency. Remember, velocity is frequency times wavelength. So you're going to perceive a frequency, which is the perceived velocity all over the wavelength. See, the wavelength's not changing in this case. The wavelength for the observer is staying the same. He's not moving at all, so he's staying the same. But the way you're going to perceive him is this. And so what I'm going to do is I'm going to plug in that as v of, so the velocity of sound and air plus the velocity of the observer all over the wavelength. Okay? But we know that the wavelength is the sound divided by the frequency. So what I'm going to do is I'm going to say, hey, f prime is equal to v sound plus v of the observer all over the wavelength, which would be v sound all over f. So all I did was I just rearranged that equation. Okay? And so the actual wavelength that exists is how fast it's traveling in the air divided by the frequency that it's being emitted. Okay? And so instead of dividing by a fraction, which we don't like, we can multiply by the reciprocal, and so I get f prime is equal to f all times v sound plus v of the observer, how fast you're moving, all over v of the sound. And so what I could do is I could rearrange this as f times v sound all over v sound. And this, remember, this is the velocity of sound in the medium that we're in this case air, plus v of the observer, that's the person moving here, divided by v sound. I just did a little algebra right there. This becomes 1. And so I get the actual frequency times the quantity 1 plus v observer all over v of the sound. Okay, that is f prime. Now, if the person is moving away, okay, if you have the observer that is moving away, then, I'll go ahead and do this, then he's doing this, all right, and so like if you're driving down the interstate with somebody going 70 and you're going 65, they're going to pass you as if they're only going 5. So if you're moving in the same direction, instead of this being a plus sign, you would have a minus sign right here. Okay? So the sound minus the observer would be the perceived velocity between you and the wavefronts. And so this formula is going to be the exact same thing, except for, so this is when you're moving into, okay, when you're getting closer to the source or moving into the wavefront, so this is closer. When you're trying to go away from the source, so away from source, then you're going to get f prime is equal to f and then quantity 1 minus v of the observer all over v sound. All right, and once again, this is the speed at which you're moving. You know, you're a moving observer, and then this is the speed of sound in air. You know, if it's room temperature, it's 343. But remember, we can calculate that depending upon the temperature. So remember, it's because this would be negative, which would make all these other ones negative too. So I can combine this formula, and I get that f prime is equal to f all times the quantity 1 plus or minus v observer all over v of the sound. Okay? And here, make sure you know this. The plus sign is when you're getting closer, and the minus sign is when you're getting, you're trying to go away or further from the source. Now let's see if this makes sense. If you get closer, as you're trying to get closer to the source that's stationary, you're going to experience the wavefronts. You're going into it. You're going to experience them faster because you're moving into them. All right? So faster means that you want this number to be bigger than what you want the perceived frequency to be bigger than this. So how do I make that happen? It's a plus sign. That's got to be bigger than that. All right? If I'm moving away from them, then by the time they get to me, I'm not perceiving them as rapidly. And so I want the perceived frequency to be lower than what I hear. And so that's why I have the minus sign. So that's the key idea. So let me go back to this. Actually, I'll just go back up here. Sorry. So in this particular case, this was a moving source stationary observer. The minus sign was when you're closer, and the plus sign is when you're getting further away. This is for a stationary source. It's not moving, but you're moving relative, and so you get this particular equation. Okay, and so to finalize, we have two equations. The first equation that we derived on the previous one is f prime equals the actual frequency all over this expression, and that's for a moving source when the observer is stationary. Okay, observer stationary. And then the other equation that we just derived is when the observer is moving and you have a stationary source. So what I'm going to do is I'm going to rearrange this equation. I'm just going to multiply the top and bottom by v sound. And so I get f prime is equal to v sound all over v sound plus or minus v source. And then that's all times f. That's another way to write it. This equation is f prime is equal to, I can multiply, this should be v source right there. I can multiply everything by v source. And so I get that's f times v source plus or minus v observer. Okay, so I multiplied that to get that. And then I'm going to divide by v source, so that if I go back, v source divided by v source is just 1, and then v observer over v source. So this equation, are the exact same thing. So this is another way to write it. Now, what we can do is we can actually superimpose these two equations together, and when we do that, we're going to get a formula that looks like this. F prime is equal to v of the source plus or minus the v of the observer all over v of sound plus or minus v of the source. Okay, and then that is all times the original frequency. So what I basically did was I took that, and that's there, and I took that, and that's there. So this is going to be for any type of situation you could have. All right, this part comes into play when you have a moving source and a stationary observer. This part comes into play when you have a moving observer and a stationary source. But here's the thing, when we do this both together, then we can handle a moving source and a moving observer. You still need to think about the pluses and minuses and how that's going to relate. We're going to talk about that in class. We'll work on this because this is a tough concept, but I do want you to write this equation down. You do not have to worry about all these derivations we did. I just want you to show where it came from, but this equation we're going to be dealing with. So what I want you to do is we're going to get some practice with this probably on Monday, but I want you to have this equation written down.